let's talk about regular expressions some more. So last time we discussed how to convert regular expression to an NFA, right? You sort of analyze it little bit by little bit. You combine together the operations in certain standard structural ways. The plus looks like a sort of two branching paths. The concatenation looks like one thing after another, and the star looks like a bunch of sort of loopy epsilon arrows. This time I want to talk about going the other way around. So can we do the other way? Question? The answer actually is yes, although it's a little harder, and we're not really going to go through the details of how you would do every little bit. But we're going to do several examples. On a fairly small example that you can, draw the diagram, it's not so hard. Although if you had a really big example, this would be difficult to do. But let's just try. So can we do it? Yes, we can. Remember Bob the Builder used to say that? Anyway, let's try to do an example. I thought we'd take an example from, this is an NFA that's on the homework. So let's make this into a regular expression. Here it is. This is NFA, which has several states in it. It's not necessary to give the states names. But this is one on the homework which you use the subset construction to turn into a DFA. It looked like this. A here, a B, and then down here, B and A like that. All right? And our job is to convert this into an equivalent regular expression that has the same language, all right? Okay. How we do it? Well, looking at the structure here, so actually this is an easy one. What makes it easy? Well, one thing that makes it easy is all the arrows kind of go from left to right on this diagram. There's a starting state and a single accepting state, and every arrow just kind of proceeds you along from the start to the accepting. But what I see here is basically, I want to think about what are the possible paths from the start to accepting. All right? What are the possible paths? And in this case, it's pretty easy to say. There are three different paths you could take, right? Go across the top, across the middle, across the bottom. And so I'm just going to describe each of those as a regular expression, right? Each path as a regular expression, and then add them together because I have three separate paths here, three separate branches. I'm going to combine them using the plus because that's how a plus works. So I write each path as a regular expression. And then in this case, I combine with a plus. Combine with plus. Plus because they are three separate branching paths. All right? So, if I were to do each path individually, can anyone give me a regular expression which represents the path going around the bottom? This is not hard. BA, yeah. Excellent. Across the middle would be ABB, right? You gotta do A first, then B, then B. Across the top is, I suppose, a little bit more interesting. What do you think? Yeah?
It's B or A, B or B, A or A.
Okay. He said, I wasn't expecting him to say it that way, but yeah, if you think about those epsilons, there's only a few different ways to do it. You could do A, B, A, or you could do A, B followed by epsilon, or you could do B, A followed by epsilon, or you could do just A. I think that's it. Are those all the possibilities?
Just B.
Just B, yeah, if I take, not just A, just B is what I meant. Yeah, thanks. Yeah, so you could write that for the top. Actually, did anybody have another idea? Actually, I was going to write it differently. Yeah. I don't want star. I like the idea of what you're saying. If I do A star, that would allow you to do something like A, and then BA, which we don't want. Yeah?
I had A or epsilon, B, A or epsilon.
Yeah, this is what I was thinking. These are equivalent. I think this second way of writing it is maybe more immediately obvious how you would get that from these arrows, right? When you see an arrow with two labels on it, you might as well just put a plus there. So the first arrow is A or epsilon. The next arrow is B, definitely B, and then the arrow after that is A or epsilon. All right. These are actually equivalent, these two. I kind of like the second one better, but whatever. Any questions about those? Anyway, my final answer then would be to add all of those together. So the NFA is equivalent to, I'm going to take the sum of all that. I'll do from, this is the top, A plus epsilon, B, A plus epsilon, or the middle, ABB, or the bottom, BA. That's it. All right. Or you could write it those other ways. This one is easy, I'll just say again, because really, when you think about it, there's only like finitely many ways to proceed from the starting state to the ending state. And we're basically just like writing down all the possible different ways you can get from here to there. And there's only so many, right? There's only 6, I suppose, if you write it this way. There's 4 ways to go across the top, and then only 1 way to go across the other 2. So we just add them all together. All right? Yes?
So why are you using or there instead of like concatenation or something?
Here? Yeah. Or is represented by doing this sort of, you can go across the top or you could go across the middle. Yeah, concatenation would be if they're all strung sort of in a big string one after another, which is, I mean, that can happen, but it's not what you see here. All right. This gets more interesting. I said this one's easy because there's only finitely many ways to get from the beginning to the end. This is more interesting when there are infinitely many ways. The only way there could be infinitely many ways is if your diagram has loops in it, right? Then instead of just one way to get from here to there, you could do some meandering where maybe you go around some cycles before you get to the end. So that's more interesting. And when there are loops, the only way to handle this in a regular expression is we must use the star. Because in a regular expression, that's the only way to get any kind of loop-like or repetition-like behavior in a regular expression. You have to use the star if you want to make that happen. So, like I said, in a very large example, this is not easy to do, but we're just going to do simple, small examples. Here is another example. So I got an A, a B, an A, like that. All right. Again, I want to try to convert this to regular expression. And we are also going to think about what are the possible paths that you can take to get from the starting state to the accepting state. Now, in this example, the starting state is the same as the accepting state, but there are several loops you can do. So, which loops can we do? I wrote da, because he said A right as I was writing the letter O. It made me write the letter A. Which loops can we do? Yeah, one is A. Just from the starting state, you can do that looped edge. So the A loop, well, as a regular expression, that would be like A star, right? Because that looped edge means I could do A over and over again if I want to. So that's how we handle the single looped edge with an A on it. That looped edge means you can just repeat the A over and over again, and as a regular expression, that would be A star. And then the other loop would be A followed by B followed by A. So the other, how would I write that as a regular expression? Yeah, ABA with the star. So it's like this, A, B, A, star. Yeah.
Why would you need to do A star B A? Because if you can like, in the beginning state, since you can do A as many times and then move to the second state, wouldn't you do A star B A?
Yeah, that's true. So it sounds like you're trying to somehow accommodate for both of these loops at the same time, although it's actually not necessary to be that fancy about it. I'll come back to this in a moment. Can we just say what's our final answer? The basic idea is you can do either of those loops as many times as you want, and you can do them one after another. Like I could do the little loop a few times, and then do the big loop a few times, and then go back to the little loop. So what I'm going to do to get the all possible combinations of those loops, I'm going to add them together and put another star. And actually, we don't even need those first stars. This is how I'm going to write it. All right, I'm describing either of those two loops. You can do the first one, that's just A, or you can do the second one, that's ABA. And putting the star outside there allows you to repeat any of them and in any order. Yeah?
When would you need to put the star on the inside then? Like have a star on the outside and on the inside?
Yeah, the star, putting a star on the inside would not change anything. So this is equivalent to if you did, for instance, like that. Those are the same, because this already means if you wanted to, you could do the star and just keep on taking the A over and over again, which would be the same as doing one of these A stars. Yeah, and this is also why, so it's also equivalent, and this is what she said before, or it's also equivalent, although this is less obvious, it's also equivalent to that. But to me, it's clearer to write it this way, just because it comes from those two separate loops. This is also equivalent just because, as she pointed out, when you're doing this ABA thing, you could, if you want to, sorry, they're not equivalent. They're not. I'm trying to be. You still need that. You still need to allow for no occurrences of the big loop. So this says I can either do the little loop or I can do the big loop, and the big loop, if you want to, you can do extra occurrences of the A at the beginning. But in my opinion, that's more confusing than just this. Is this still not right? It needs to be, okay, it needs to be that. Yeah. Is that what you were going to say?
I had A star, A, B, A star.
A star, A, B, A star. Where's the last star?
Enclosed in ABA.
Yeah, this means you do the little loop sometimes, and then you do the big loop sometimes, and that's it. This does not allow you to do the little loop after the big loop, which you need to allow. Anyway, these are all variations. In my opinion, that's the best one. These other ones are also correct, I think, but they're more confusing to me. Yes?
So why do you need the extra A, like in the correction you just made where you did A star ABA?
Over here?
Isn't A star BA? Like wouldn't that still account for doing one A and then BA?
Yeah, but if I leave this little A out, that would allow you to skip the A's entirely, right? Like if it was just A star BA, this you could do none of the A's here, and just BA, which is not good enough because you need to do at least one A there to go around that loop.
Okay.
Yeah. There are many different correct ways to write this, although the one in the box there, in my opinion, is the best way. I'm ready to fight about it. All right. Let's try another one. So this involves how I would suggest you look at this is, I don't know if I needed to erase that. This one's actually wrong. How I would look at it is figure out where are all the possible loops, and then just indicate those, connect them with pluses, and put it all inside of a star. All right? Because you can repeat either this loop or that other loop, and you can keep on doing them in any order you like. So we basically sum the loops inside a star. This is basically what we're doing. I'll put that in quotes because this is a little informal, and there are some examples when you have to think a little bit differently. Another thing that made this one a little bit easier is the starting state is the same as the accepting state. That's typically not going to be the case, and you have to modify things slightly in those other situations. So let's try another one. How about this one has an accepting state? It's the same as the previous one, only it has this extra like B edge before you. Sorry, I didn't mean to make it the same. Let's do just like this. All right. Again, I think first of all, what are all the ways I can get from the starting state to the accepting state? And in this one, I would say you do B, and then if you want to, you can do a bunch of loops, right? So that's how I'm going to think of this. You do B first of all, and then you do some loops. So my answer will begin with B, because you got to do B first. And then I'm going to do what we did before, which is sort of sum the loops inside a star. So maybe put some parentheses here. There's going to be a star out there. And right inside those parentheses, I'm going to write all the possible loops you can do from that state that you get to after the first B. And what would that look like in there? A. That's one. Yeah, A or AB. And I think that's it. Those are the two loops that you can do from that state right there. All right. I think you can imagine this could get quite complicated if you had a really big diagram with many loops in it, and especially if you had sort of overlapping loops or something. Like I've drawn these ones always so that, you know, there's two loops here, but they don't really interact with each other, but you could have more complicated behavior. Anyway, I got some for you to try. See if you can try. If you look in the book, actually they devote what is basically an entire chapter's worth of material to doing a very detailed description of exactly how you do this in all cases. And in my opinion, it's a little more trouble than it's worth. So we're not going to go through the super detailed algorithm. Although if you're interested, check it out. Here's one. I got two for you to try. There's one. And this is very similar to the previous thing. Another one. All right. See what we think. I'll come around in a moment. See how you're doing. also do yeah, that's excellent.
Right.
Mm-hmm.
Yep. It's
Yep. Yeah, so actually once you put there, you don't actually need this, because that is the special case of this.
Oh, because this would be zero. Right. Why don't you give me A's after this?
For those things? Yeah, because you can get those from here. So like, you can go through the star again, put A's in. Okay?
Yeah. I think that
This is the A.
yeah.
This one. Yes. Yeah, we'll put on this. You need at least one A here. You get to A star, but
Oh,
as well.
that's right. Okay. Another A.
Yeah. You good? Yes, that's good. Alright. Looks great. This one, okay. See, that's good. Good. This needs to be a little fancier. AAB is supposed to go here. But you could also do like A. As a little something. Yeah, that's good. That's great. Looks like people are doing pretty well. Let's chat. You doing all right?
Just as
Mm-hmm.
this project kind of
Yeah, we'll see. There are, as you know, many ways that you can do these. I think the best way to write this one is B. This is what I ended up seeing people doing. B, and then there are basically two loops. There's this one here, and then there's this one here. This is actually an example where you have sort of a sub-loop inside of a loop, right? It's basically this, A, then B. But while you're in there, you can do a bunch of A's also, which is why there's an A star right there. I saw pretty much everybody got that as I was going around. The second one, what do you say? Anybody want to tell me what they got? What do you say?
So I have, like, in one big parenthesis, I have A or B,
Okay.
and then I have or B, like in another, yeah.
Uh-huh.
And then that's all under a star, and then I have A.
All right. Did you mean B here? B squared? I think that represents this little guy, right?
I was thinking just or B. Do you need the second B there? No.
I think you do. So this A plus B represents this loop, right? And then this BB represents this loop, BB.
and we just away this week, this one.
And then you put a star,
Yes.
and then you said AB.
Yeah.
That's the rest of what you said. Yeah, I think this is how I would have done it. Now, I would say actually those parentheses around the A plus B are not really necessary. But there is like an associative rule for pluses. You know, when you're combining things with pluses, certainly with numbers, you wouldn't put parentheses here. Although they're not wrong, you might as well just do like this. But what were you going to say? I think.
Can we just remove the leading?
Yeah, once you do this, actually this BB is redundant with this B, right? This says since it's inside the star, this means I can do repetitions of a single B if I want, or I can do repetitions of two B's. That doesn't really matter. So actually this, once you write it that way, you might as well simplify it to this, if you're in the business of simplifying. Yeah.
Can't you also do like once you do two BBs or A or B, can't you also go to the opposite side and then do AB?
To the, say
So
that.
like if you do BB and then can't you also loop around A or B
Yes?
and then do AB?
Yeah, that is allowed with this star here. It means you can do this thing, and then you can do this thing, and then you can do this thing again if you want.
Okay.
Yeah. Yeah. So, these are all equivalent. I would, to me, like, this one is the most clearly correct based on the picture, although the others are equivalent to it. And if I were writing these answers just sort of like for myself, I would typically try to write it in a way which is most obviously correct. Now it's true you can simplify after the fact, but once you get down to this point, it becomes less obvious, like exactly how is this capturing what's in the picture. The fact is, really, the picture is already kind of redundant. This BB here doesn't really do anything in light of the fact that there's a B looped edge over here. So even the NFA itself can be simplified in this case. All right. This is more or less how you convert a NFA to a regular expression. These are all kind of small and easily workable examples. In a much larger example, this can be a lot harder. But like I said, I don't really want to get into the details of this. All right. In any case, I hope that you will believe me if I tell you. You can read the long and detailed proof in the book. Any NFA can be converted to a regular expression. Even if it's very complicated, I said there may be infinitely many paths from the starting state to the accepting state, but because the diagram is finite, there's not infinitely many loops, right? There's only finitely many loops that you can do. And so you should feel like, yeah, in theory, I could just write down all the loops and put them all inside of stars, and you would be able to make a regular expression out of it. It might be super big, but it should be possible to do in theory. And it is true. Any NFA can be converted to a regular expression. All right? So actually that means if you put this together with what we did last time, we can actually go, back and forth, right? Any regular expression is convertible into an NFA and vice versa. And what that means in terms of the languages that you can do with the regular expression, it's the same bunch of languages as the ones you can do with the NFAs, right? There are no, it's all just regular languages. So what this means, and this is actually, there's a name for this. This is a theorem called Cleany's theorem. It says that L is a regular language if and only if L can be generated by a regular expression. And this is why they're called regular expressions, or maybe why they're called regular language. I'm not sure which one was called regular first, but they're both called regular because they are the same type of things. A regular language, this is like the third different way of describing what regular languages are. You could say regular languages. If someone, approaches you on the street, in the club, and says, hey, what is a regular language? You could say, well, it's any language that you can make with a DFA. Or you could say, it's any language you can make with an NFA. Or you could say, it's any language you can make with a regular expression. They're all the same concept. All right. Great. Are we ever going to talk about something that's not the same? Yes. This is the last of the new thing which turns out to be the same thing. All right. I know that's a little anticlimactic, but all the other things that we're going to talk about going forward in the class are all going to be about non-regular languages. Remember, there are non-regular languages. We got 20 minutes. We can start talking about this. There are non-regular languages, and we had one example that we actually demonstrated was not regular. And it was, anybody happen to remember? You will remember this example very well in the future. A to the n, b to the n. This is not regular. We actually proved this. Although I took I went to lengths at that time to tell you that the proof that we did was really very much a special case for this particular language. We did a proof that worked for this language, but we did not talk about a general purpose method for showing that a language could be non-regular. You have to, like theoretically speaking, what you have to do is consider all possible DFAs or NFAs or perhaps regular expressions and show that you cannot possibly make this using any DFA or NFA or regular expression. From an abstract point of view, that's not an easy thing to argue at all. You have to somehow consider all possible NFAs, which is not an easy thing to do. But I want to talk about a general purpose method, a general method by which you can show that a language is non-regular. A general method to show a language is non-regular. It's a little, I wouldn't say hard, but it is a little complicated, and we're going to start on the journey today, and we're not going to actually get there until maybe after the test. I mean, the test is pretty soon, I suppose. A general method to show a language is non-regular. It involves, I'm about to say a word you never thought I was going to say in this class. It doesn't really mean the same thing that it means in other classes. The derivative. Can you believe it? Can you imagine what that could possibly mean in this class? It doesn't mean the derivative from calculus, but it's called the derivative because it has some similarities to the derivative from calculus, even though it's not, the limit of the f of x plus delta x or whatever. None of that stuff. All right, but it involves the derivative. Specifically, this is called the name for this special type of derivative, which is used in this when you're talking about alphabets and languages. It's called, I want to make sure I spell it right. It's this, B-R-Z-O-Z-O-W. This. It's this kind of derivative. This is what they'll say in the club. They'll say, the derivative, what? Well, no, not the derivative from calculus. The Jazovsky Derivative, something like that. This is a Polish name. Anybody speak Polish out there? The B sounds like a B. RZ, as I understand it, sounds like SH in English. So it's like Jazovsky, something like that. And the W sounds like a V. Paul Baginski speaks Polish fluently, so he gave me a little lesson on how to pronounce this. I typed it into something on Google, it wasn't Google, but it was some website that will pronounce words for you, and I typed this in, and it said Jazovsky, which is not how you say it. Paul set me straight. Anyway, we need to talk about the derivative a little bit. And as we begin to talk about this, it will seem to have nothing at all to do with showing that something is not a regular language. But it turns out that the idea of the derivative is super useful in showing things are not a regular language. Maybe I'll say at this point, I don't know if you care, but this is the business about the derivative is not in our book. Our book has a completely different approach to showing languages are not regular. So the book uses something called the Pumping Lemma, which is a very strange, this word lemma is kind of like it means the same thing as a theorem, but usually a lemma is like a smaller stature than a theorem. It's like a less important thing which you use the lemma to prove the theorem, something like that. But anyway, the book uses the pumping lemma, which I was always a little dissatisfied with the pumping lemma. It's very complicated to write it down, even though the idea behind it is not so complicated, but it's very, very complicated to talk about. The derivative is a much simpler thing, and I like the approach with the derivative a lot better. And I actually, I first learned about the Jazovsky derivative in a tweet that I saw someone disparaging the pumping lemma. They were like, man, I hate the pumping lemma. I love the derivatives instead. And I was interested because I also kind of hate the pumping lemma. It's not terrible, but it's like overcomplicated. Anyway, we're going to talk about the derivatives. So I don't know if you like to read along in the book, in the textbook. You will not see stuff about the derivative in the textbook. Anyway, here's what the derivative is about. The derivative is related to the question, and this is a weird question. Like I said, this will not obviously seem to have anything to do with showing something is not a regular language. But the derivative is related to this question. What happens if you have a DFA or an NFA? What happens to the language of my machine of, let's just say NFA or DFA, doesn't matter. What happens to the language of an NFA if I move the starting state, but keep everything else the same? This is not a question that we've ever asked, and by itself is not obviously a useful question. I mean, it's sort of a curiosity, I guess, but it turns out this is important. So here's an example. Let's see if we can look at it. Actually, what I'm about to draw is a DFA. It doesn't really matter. So the starting state is there. All right. Boop, 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 boop. Okay, here is a DFA. And let's call this one M. M is this machine, all right? Can we say what is the language accepted by this DFA? It looks kind of complicated, but it's not so hard to look at. Like this state right here is a rejection, like a permanent rejection state. So the only strings that are accepted are the ones that manage to stay out of this kind of black hole. They go around here maybe, and they go there. Anyway, can we say here the language of M is, we'll write it as a set, or maybe, I mean, you could write it as a regular expression if you wanted to, but what do you think? A, B? It's not, it's a little more.
A to the n where n is the multiple of 3.
Yeah, AB to the n. I'm going to write it, so he said AB to the n where n is divisible by 3. I'm going to say it this way. AB cubed to the n, right? Which is equivalent to what he said, although the n is different. So in order to be accepted here, you got to have an A first, and then followed by a bunch of B cubes, right? Or a bunch of B's taken 3 at a time. Okay, this is the language. Now, what I wanted to ask is, what happens if we move the starting state? So instead of this picture here, what if we move the starting state? And I'm going to think of it as starting, the starting state right now is here. And I'm going to try and move it sort of within the diagram. We could either push it through this A edge, or we could push it down through this B edge and end up the starting state here, or end up the starting state here. So I'm going to say, what if we move the starting state through the A edge? All right, what happens then? So I'm going to call that, I'll draw this picture again. Maybe I'll copy and paste. I know this is hard if you're using paper. Oops. If I do it slow enough, you can catch up with me. All right, same picture. I'm going to call this one N. Only its starting state is now that one. I push the starting state through the edge labeled A. So what if we move the start state through the A edge? Can anyone say, like in basic words, what happens to the language when we do that? Yeah, every string here which had an A at the beginning, that A just goes away. And otherwise the language is the same. So now the language of n is b cubed to the n, right? Where n is in n. So the effect, when I move the start state through the edge labeled A, this has the effect basically of deleting a at the beginning of every string in the language. All right? Do you have a question? Did I mess it up? No. This has the effect of deleting a from the beginning of every string in the language. I'm going to write that. Moving the start state, through the A edge has the effect of it deletes A from the start of all of our strings. All right? That's what it does. What if we moved it down the edge through the B? Then what would our language be? So how about, I will say, move it the other way. What happens then? Get my picture? So instead of up here, I'm going to put it down here. That's the starting state now. Can you say, what's the language now? I'll call this, I don't know, P. Yeah, this one actually rejects everything. The language, if you had to write it, would be the empty set. There are no strings that are accepted, right? How can we make sense of this? Were you expecting me to say, if I push it through this edge, then it just deletes a B at the beginning of every string? That's what you wanted me to say, probably. But if you think about it, the original language didn't have any B's at the beginning of every string. So this is what happens. If you try to delete a B from the beginning of strings which don't have any B's on it, they go away entirely, all right? So this is what happens here, is that it's as if we are skipping over any initial B's, right? But our original language, L of M, was, this, A, B cubed to the N. This has no initial B's. So when you do it in this case, you just end up with nothing. So we end up with nothing. All right. There's a name for this operation of you start with a whole language and then you get the same thing, but you skip over all the initial A's or all the initial B's. That's called the derivative. So the way we write it, it's about time to go, but let me just say what we're doing by, say, skipping the initial A's is really like this. We are considering all x such that ax is in the original language. All right? What you do is you take all the things which were in the original language, which originally did begin with an A, and then you throw the A away and you take just what's left. All right? Or you could do this with a B. You could take everything in the original language which started with a B, and you throw that B away, and you consider only what's left. This is the set that you get when you sort of skip over all the initial A's, and you only consider what's left over after skipping an A at the beginning. All right? And that right there, that set is called the derivative. So this is the Jazovsky derivative of L with respect to A. You gotta think of these as like partial derivatives. You can do it with respect to A, or you can do it with respect to B. You can do it with respect to any letter in your alphabet. This is the derivative of L with respect to A, and this is the definition, and we write it this way. Derivative with respect to A of L. And the definition, this is the definition. It's just what I wrote up there. It's all strings x such that AX is in L. A little strange, but basically what it means is you think of all the things in L which started with the A, and you just take the A away from them. Anything in L which did not start with A, you don't even consider at all, right? There may be many strings in L which don't start with A. They are not part of this at all. This is called the Jazovsky derivative. So in our example before, so for L being the set of all things that look like A, B cubed to the n, the derivative with respect to A of L is just B cubed to the n. You take all of those things and omit the A's that are at the beginning. But the derivative with respect to B of L is the empty set. That's because nothing in that original language started with a B. And so when you consider all things from here that are of the form Bx, and then you take only the x part, well, no strings in here are of the form Bx. All right? This is how you do the derivative. So for instance, I'll just end with a silly example. Let's say if L, this is, I suppose, like a real world example. If L was the set of all real English words, what does dA of L look like? Can anyone give me an example of something? String in derivative with respect to A. It contains strings like, what do you think? Yeah?
All letters beside A.
Can you give me a specific example?
Zoo.
Zoo?
Yeah.
I don't think zoo is in this set. This would be all strings so that, what do you say? L what? LLO? W. Yes, this one is in there. LLOW. Why is that? It's because since ALLOW is a real word, right? The derivative consists of all the real words that started with the A, but you take the A away. All right? Like LLOW, because ALLOW is a real word. Or something like PE, because ape is a word, APE, or divertisement, right? There are many, many things in the derivative with respect to A of L.
It's empty.
MT? Oh, you mean the empty string? Yeah. That's a great, I thought you meant the letter M and the letter T. The empty string also is there. That's because A by itself is actually a word. And so if you omit the A from the word A, you're left with nothing, which is the empty string. Yeah, great. All right, we will eventually tie this into non-regular languages. We'll wait till next time, I guess.